Hi there. Today we'll talk about switch transformers, scaling to trillion parameter models with simple and efficient sparsity by William Fetus, Barrett Zoff, and Noam Shazir of Google Brain. So as you can see right off the title, we're going towards trillions of parameters. GPT-3 had 175 billion parameters. This paper claims to have a model with 1 trillion parameters. Now, is it really 5 times bigger or 10 times bigger than GPT-3? That's a debatable question, because the trillion parameters are not used in the same way as in a classic transformers. They are used actually in a sparse way. That's why the word sparsity is in here. And the way they are used in a sparse manner is this new architecture called the switch transformer. It's not entirely new. It's built on mixture of experts. In this paper, that's also called MOE. That has been around for a while, and we're going to see what that is. Now, on a high level, switch transformers takes mixture of experts to an extreme, in that it is a transformer, and the feed-forward layer is divided up into these experts. And the switch transformer only routes each token to one expert only. That's the sparse part. So the mixture of experts previously, they always claimed you need at least 2 experts in order to get a stable training signal. The switch transformer manages to get it down to a single expert. So it's like a hard routing of information to just a single endpoint per layer of each token. So in that means you can now scale the experts, and you can scale the number of parameters in the model without making the model compute more. That's a very special notion. So you can up the parameters of the model, but if a forward pass of a data point will still have the same amount of flops that it needs to forward propagate through the network. Very special architecture right here. So yeah, that's why I'm saying trillion parameters, not necessarily comparable to the 175 billion parameters of something like GPT-3. So how do they do it? Because previously it was claimed it was unstable. They have new ways of making the training stable, such as selective dropout, selective casting of parameters to different precisions, and a better initialization. So that's the high-level overview of the paper, and we'll dive into it. We'll explore kind of what mixture of experts is and how the model works and what turns out. It's a very long paper, as you can see. When papers have a table of content, that's a lot of fun, but it's a lot of engineering as well. And we're mostly interested in the model here, what it can do, and how does it sort of fit into the big world of transformers and language models and so on. Last thing I want to say, trillion parameters is, it's a catchy title. Most of the paper, they don't work with trillion parameter models. They work with models in the order of billions of parameters, and at the end, they build a model with 1 trillion parameters. It doesn't do as well as their models as their smaller models. They also, it feels like they don't put that much work into it, because it's probably also quite fuzzy and expensive. But just know we're not going to have trillion parameter models around anytime soon just yet. Interesting fact, the original ResNet paper also built a 1,000 layer convolutional neural network. Even though the ResNets we have today, they are maybe 50 or 150 layers deep, they did build a 1,000-layer model. So maybe compare it a bit to that one. It's just like, we can do it, not necessarily we need to. So here you can see something they discover. The curve on the left is very, very known to people that are in the language model game, let's say, or in the let's scale up AI game. And that is, as you increase the size of the model, the loss will go down. And that's loss, as I understand it, so that's test loss. I believe that is perplexity. So scaling properties, Exactly. That might be perplexity or test loss on some downstream task. In any way, as you scale up the model parameters, the model gets better and better and better. The interesting thing right here is twofold. First of all, I believe they do hold the data set constant. So the data set is always the same. The amount of compute you put into it, the amount of either number of steps or time, is also always the same. And in this specific case, the amount of flops per forward pass is also the same. The only thing that changes is the number of parameters. Again, it's very special to have a model where you can scale up the number of parameters, yet the flops required to forward propagate stay the same. So you can see here that there is a almost unhalted decrease here. It flattens out a little bit towards the bottom, though that is does not necessarily mean it will ever flatten out before it's at zero. It will approach zero, I guess. So, and you can see that they scale up the model quite a bit, and also their main comparison here is the T5 base. So that's the text-to-text transformer. By the way, if you don't know what a transformer is or what a language model is, it's best you go back to my earlier videos and look up like the GPT-3 paper or the Attention is All You Need paper. I've made videos about lots of these things. I assume that you know them. You can see right here that if you compare to number of training steps, for example, these switch models, all of them, no matter how big they are, they provide massive gains over like something like a T5. And they also do this in time. So this paper is very much about trade-offs. You do require more storage for your weights. So you have to have more memory, more RAM. However, that memory can be distributed. It can be sharded because they use this mesh TensorFlow library to implement the switch transformers. And because their model has this sparsity, they can efficiently shard the model. So you trade off more memory, which can be sharded, but what you gain is training speed, both in terms of time and number of training steps required. So you are much more efficient. Note that all of this holds in this super large regime, right? They say they've also discovered these speedups in smaller models, but as far as the paper is concerned, we are talking about millions, hundreds of millions of parameters, billions of parameters, even to trillion of parameters, together with these giant corpora of text. So that's sort of the regime we are in, and the results do not necessarily transfer down to the lower scale problems that you might face with your lonely one collab in the corner. All right, so in a transformer, a transformer is nothing else but a bunch of these layers right here. This is in itself a transformer layer in its basic form, and it consists of sort of two parts. It consists of this self-attention right here. Now that's the standard transformer self-attention. That's what was introduced in Attention is All You Need and what's been used ever since in all the transformers. This one right here is an as I understand it, a language model. So this is very standard. However, after the self-attention, you have this feed-forward layer. Now, usually, what you do is you have an input sequence, and you transform that through multi-head attention into another sequence right here. Okay, and then what you do is you take each of these things and feed them through a feed-forward layer. And as I understand it, this feed-forward layer is simply a regular feed-forward layer that you would find in a neural network, and you pass these things individually. So this here, it's a vector. You pass it through here, and boom, that becomes the next layer representation. This thing right here, you pass it through as well, boom, that becomes this one, and so on, right? You pass them individually to get the next layer representation. So this part right here, the attention part, it sort of aggregates information and relates the individual items of the sequence to each other and transforms them into, a new sequence where sort of every token can gather information from every other token. That's what the attention mechanism does. That's step one. In step two, every token is isolated. Every token is for itself, and the feed-forward layer simply determines, what's given given token number one, what is, given its representation in this layer, what is the best representation for the next layer, okay? So that's token number one of the next layer. So the multi-head attention is kind of relating tokens to each other, and the feed-forward layers, they are relating layers to each other, okay? So up here you would have the next multi-head attention layer. So you can see the feed-forward layer as sort of translating from one layer to the next layer, right? Saying, you come from this layer, I'm going to translate you such that the next layer understands you. And that happens on a token by token basis. Now you can see it's always the same feed-forward layer for all the tokens, right? The tokens are sort of treated like a batch of samples. The idea of this switch transformer and also of the earlier mixture of experts transformer is that it might not be a good idea to have only a single one, right? This is the only feed-forward layer. It's the same for all the tokens. It might actually be a good idea to have a couple of them that sort of specialize in different things. So what could that be? In a basic world, this could just be like one for nouns, and this could be a feed-forward layer for verbs, tokens that are verbs, tokens that are adjectives, and sort of maybe here is like punctuation tokens, right? You might think, well, if you are a noun token, the next layer might want to look differently at you than if you are a punctuation token, right? So this translation from one layer to the next layer can now happen dependent on what the token represents, right? Now we of course, first of all, we don't have these annotations, and second, it's not necessarily that we want to always divide it by noun, verb, adjective, punctuation. Ideally, we want to learn this routing, so we simply want to say, look, instead of just one feed-forward layer, we give the model 4 feed-forward layer. Feed-forward layer 1, 2, 3, and 4. And for each token, the model can decide to which of these feed-forward layer it sends the token to. So here you can see this is a token. Now, we are dealing with word pieces. Let's just say the word more. I was thoroughly confused by when I saw this, why does it say more parameters? But here, it's the string more, right? And the string parameters. And these are in the vocabulary, and they get an embedding vector associated with them. So that's what's going on here. Then they go through self-attention, as you can see here, both go through self-attention. And then each one of them is routed to one of these 4 experts. Now the one here, the one on the left and the one on the right, these are the same experts, right? They're just duplicated visually here. But these would be the same weight matrices in there. So you have 4 feed-forward layers in this layer, and each token can be routed to any one of them. And this routing here, this is learned. So in here you have a matrix, they call it like WR, and using WR, you simply do an inner product of WR with your input right here. Let's call that H with your input H. I guess they use H for a different thing. I think they call this X again. So you do this with X, and then you get H, which is your routing, and then you simply build a histogram. You normalize the histogram, I think, with a softmax, and those are your routing weights. So it's very much like another attention mechanism, except that the queries, this thing here, these are like the queries. These are sort of the queries of this attention mechanism. And this here, these are the keys and the values. So let's go keys and the values of this attention mechanism. The queries are just learned. So the queries are not dynamically generated. And the keys and values, they are not, it's a weak analogy, but you can sort of think of it like this. So there is this routing mechanism, and it decides where a token goes to. Now, as you can see, the router is soft. That means there is never a 1 or a 0 right here. There's always kind of a number in between, but they hard clip that. So they hard clip it. They just route it to the maximum. As you can see here, number 2 is the maximum, and they just route it to number 2. They don't route it proportionally or anything. They just take argmax and they route it through. They do multiply the output by the actual number that they got out here. So if the router is unsure, then the output is less. If the router is sure, the output is more. But this hard routing is what's the key right here. And that means, before you'd have one feed-forward layer. So any token that goes forward goes through one feed-forward layer. If you do a mixture of experts in the classic sense and you route it in a soft way, you now have 4 feed-forward layers. So every token goes through 4 of these computations. So you've basically multiplied the amount of computation by 4 because you've multiplied the amount of parameters by 4, right? You have 4 times as many parameters. Now, when you do this argmax routing, like the switch transformer, you have multiplied the number of parameters in your model by 4, but any token will still only incur 1 feed-forward layer. That means you keep the amount of computation that you do per forward pass the same. And that's sort of the key right here. So now they can scale up massively the number of experts while still keeping the amount of flops the same. And notably, you also don't need any data transfer in between the experts. Every expert can receive their tokens and then do their independent work. So you can efficiently shard this across many, many machines. This is how this looks. So in this case, you have 3 experts and your sequences are of length 6. So you want to sort of route each token there, and there can be overflow. Like every token is independently routed, so it can happen something like this, that a token, like 3 token gets routed to 1 expert, but it only has space for 2 tokens. And they have some tricks, like they have this capacity factor right here, or they can reroute. These are very much engineering things, which are important, but they don't change the sort of final result. Now, I want to go down here where they have a display of this sharding, more like an explanation of this sharding, which I think is very illustrative. So what do they essentially do? If you think of many machines, you have 16 machines. So each little square here is 1 machine, okay? Here are the different ways of how you can shard a model. And model sharding, we are not going to build a machine anytime soon that can hold 8 trillion parameters. Just not going to happen, okay? So you need to somehow shard the model or the data or both. And these are the different ways how you can do it. So if you use data parallelism, that is the easiest. That is also directly built into things like PyTorch and so on. What you do is, so the top row shows how the model weights are split, and the bottom row shows how the data is split. So how to read this is, when you do data parallelism, the weights are split such that each of the 16 cores has the same weights, you see? So these weights right here are the same as these weights, are the same, they're all the same. So this is sharded, the data is run, so that you take a data set, you take a batch of data, and now you distribute. This data point goes here, this data point goes here, this data point goes here, and so on. You distribute the data, and you do the forward propagation, and at the end, you sort of gather them again, right? So you gather them together. Again, because you have to, calculate your gradient. Okay? So that's data parallelism. The model is spread out, and if you want to do an update to the model, then you need to communicate around these weights. Okay? So all these different pieces have to then communicate with each other when there's a weight update. If you do data parallelism, here is how the data is split. We've already seen this. So this piece of data is split over 16 cores. So you can see like this core right here only has this little piece of the data and not all of the data. On the other hand, you can do model parallelism. In model parallelism, you can see it's exactly the other way around, namely that one core only has a little piece of model, right? But every core gets all of the data. So this data here, the bottom row is data, all of the data. The point here is that if you do model parallelism, that's what you do when the model itself doesn't fit, right? Over here, the model fits on your machine, but not the whole batch at the same time. Model parallelism you do when the model itself doesn't fit. What you have to do is you have to take your data, right? And you have to send it sequentially. So maybe this is the first layer, like that's layer 1 weights. And then you have to compute layer 1, and then you have to send it to layer 2, and so on. So you have to send it sequentially through the sharding of the model, right? Because you want to forward propagate through all of the model. This has very, very much of a cost of communication. You can build very big models, but it comes at a cost, right? And at the end, you get your Y and you calculate your loss and you backprop again backwards through the whole thing. You can mix them, right? You can do model and data parallelism. So here you can see that the weights, so this is layer 1 weights, layer 2, layer 3, layer 4. And here again, you have layer 1, layer 2, layer 3, layer 4, and so on. So you can mix the two in that you can have model and data parallelism if both your model and also your data don't fit in a single machine. And you can see here that this upper left part receives the same data, but this here receives different data, right? So you split your mini batch into 4 different parts, and you send the first part up here, like that's data 1. You send that up here, and that goes through the model in this sequential fashion. You send data 2 right to here, and so on. So we mix the two. Now, in expert and data parallelism, that's what they do in the switch transformer. So this here is the switch transformer, and this here over here that's the switch transformer 1 trillion. So for the 1 trillion model, they actually need to mix all of them, but you want to, if you can, you want to avoid model parallelism. Model parallelism is really the thing that kills you because of the very high communication cost. So in the switch transformer, they have expert and data parallelism. What does it mean? So the top row is how the model weights are split, and you can see the weights are split, but the different color means that they're different weights. So here are weights number 1, weights 2, weights 3, weights 4, and so on. Now we've already had this over here, right? Different weights in the model parallelism case were split over different machines. However, if you look at the data is also split, and the weights, they're not the same. And these are exactly these experts. So experts, this means that, this piece of data here only goes to this expert and then to the output. This piece of data right here only goes to this expert and then to the output, right? There is no communication between the different experts, whereas here you have this super high communication. Okay, so you can see you can scale up the experts as you scale up your data, as long as each shard of data is routed to only one expert. And then, of course, you can mix the expert model and data parallelism if not even a single expert fits on a machine, right? If that's the case, you need to, again, you do model sharding on the experts. All right, so the switch transformer, as I said, this here is the switch transformer that the most of the paper is about. And now we can dive into the results. The results are pretty spectacular. They mostly compare, as I said, to T5 base and T5 large. And as you can see right here, the switch model has significantly more parameters. So 7.4 or here 26 billion parameters compared to not even a billion of T5 large. Yet the number of flops is matched. So they build models where the number of flops for a forward prop is matched, but the number of parameters are higher. So, you know, it is somewhat of a fair comparison, right? You have the same amount of compute done per forward prop, and now we see what does it help to just have a gain in parameters. And it turns out it helps a lot. You've already seen that we get these massive speedups, massive sample efficiencies over a dense model. So this we've looked at exactly in the intro. They also have benchmarks on, let's see this down here. They also have benchmarks on multilingual data set, and you can see in every single language the switch transformer gains on the dense transformer by quite a bit. So this is log space, as you can see, and it's quite impressive actually. And these gains are in time as well as number of steps. So that's pretty cool. So as I said, the trade-off here, of course, is that you need more machines. You need to actually add more machines. And you can see this largest model that they built is this switch XXL, which is matched in flops to the T5 XXL model, yet has many more parameters and beats the T5 at log perplexity and, as I understand, in downstream tasks by quite a bit. They also built this trillion parameter model. It is not as good, mainly because as I understand it, they just want to get to 1 trillion parameters. And I think it's, training isn't really easy at that size. So they scale it down. As you can see, it has less number of heads, less number of layers, but the number of experts are way up. So that's how they scale to 1 trillion. And the results are, better than the T5 XXL, which is impressive given that it has less flops per token. However, it is still worse than the switch XXL. So the trillion parameter model, it's still not everything to have a lot of parameters. You actually need to do good trade-offs. And here they've traded off too many parameters for, less number of heads and less number of layers. And that hurts again. So, very, very interesting stuff right here. The last thing I want to look at is their tricks for getting this to work. So they detail 3 tricks for getting this to work, and they are right here. 3 tricks, how they can do this, and people before them have said, no, you need at least 2 experts, otherwise it's unstable. So they do selective precision with the large sparse models, which means that if for some of these computations, it pays off to do them in higher precision. You don't want to send around these float 32 precision things. You don't want to send those from machine to machine, right? So you have your input, you have your multi-head attention, And then here, again, this is whatever, x prime. And then you send that to the experts. Right, here are the different experts. And then you send that back. And that's y, okay? Now, you don't want, this here is communication cost. If you were to send around float 32 vectors, that's a lot of data that you have to transmit. So you'd rather send around 16-bit precision, right, as they do right here. However, if you do 16-bit precision, the whole machine learning part doesn't work as well. So what they do is as soon as a vector arrives here, this is in 16-bit, they scale it up, they cast it to a 32-bit vector, they calculate using the 32-bit vector, 32, and then they cast it again to a 16-bit vector to send it back. And that seems to work. So they do selectively casting the precision up, and also they do selective dropout. That's down here. So they do expert dropout, which means they don't apply dropout to the whole network uniformly, as you would do normally, but they say they can do a much larger dropout rate at expert layers. And that makes a bit of sense because each expert is only used very sparsely, so it makes sense to up their dropout rate because, in the end you might drop out as much signal from a sparsely used expert if you raise the dropout rate than you do from a densely used layer with a smaller dropout rate. And the last thing is that they simply do better initialization. So they find if they scale down the initial scale of the original transformer by a factor of 10, that leads to a lot more stable training. It's astounding that after so many years, still something like initialization can, make or break such a model. That is just insane to see. So there's a lot more to this paper. They do a lot of downstream tasks. They also talk a lot about, this is not only this model, they do a lot of optimizations under the hood. They use mesh TensorFlow and so on. It's clear that a lot of work has gone into this. And interestingly enough, they can also distill these models. So what they can do is they can take this large model and they distill it to a model that is as big as T5 base, a dense model. So they go from a sparse large model and they distill it into a dense model that is equivalent to T5. And they do outperform T5 if it were trained from scratch. And they gain up to something like 30%. So 30% of the gains they made from here to here, they can retain by distilling it down. And they say they can distill it down way over 90-95% of the model, which is also pretty interesting and, pretty cool because then you could sort of distribute the trained models around and people could use them. All right, so that was it from me. Definitely check out the paper and all the experiments, downstream tasks, and so on. It's a very cool paper, has a lot of cool experiments. There's code, at least pseudocode, and that was it. Thank you. Bye-bye.